Hi, my name is Emilio Callejas Lopez, and in this video, I will walk you through the thermodynamic investigation our team performed to analyze the reported shootdown of an F-16 fighter jet. Our goal was to determine, using the first law of thermodynamics, whether the missile described in the report could have physically reached the aircraft under stated conditions. We first began by breaking down the F-16's low bypass turbofan engine. We did it into steady float components, which were the diffuser, the compressor, the combustion chamber, the turbine, and the nozzle. For each part, we applied energy balance equations to find how temperature, pressure, and velocity changed along the flow. To start, we used isentropic relations for compressive flow. This gave us the total temperature and total pressure at the diffuser inlet when the aircraft was cruising at 0.7 Mach and 1500 meters of altitude. These relations allowed us to estimate the temperature rise across the fan and the compressor and the mechanical power they demanded, roughly 35 megawatts. We also calculated the mass flow rate using the given bypass ratio, separating core and bypass air. And next, in the turbine, we used the required compressor fan work to find the temperature drop needed to supply the power. That gave us the outlet temperature leaving the turbine, around 1100 Kelvin, consistent with typical military turbofan operations, so that was a good sign. This stage illustrated how energy extracted from the hot gases powers the compressor and the fan, closing the Brayton cycle loop. Finally, we analyzed the nozzle expansion using the conversion of enthalpy into kinetic energy. The resulting exhaust velocity was approximately 1260 meters per second, which is nearly Mach 3.8, which also means that it's almost 3.8 times faster than the speed of sound. This is critical because the surface-to-air missile reported, which was the 2K-12 CUF, has a maximum velocity of only Mach 2.8 or about 826 meters per second. For these calculations, we can see that the jet exhaust gases were moving significantly faster than the missile itself. While that doesn't mean that the plane was literally flying at Mach 3, it does show that the missile's closing speed relative to the aircraft's motion and engine output may have been insufficient to achieve reported direct hit. This discrepancy points towards another possible cause for the loss, such as a mechanical failure, maybe an aerodynamic stall, or a control system issue occurring after the evasive maneuver. What I learned personally from this project is that thermodynamics isn't just theory, it's a tool for interpreting real-world events. By following the first law of thermodynamics and applying energy balance principles to each component, we transform abstract equations into clear picture of how the F-16 engine performs under stress. It also showed me how sensitive these processes can be, because even when we change the assumptions from the real world event, the results were almost every time realistic. Based on the thermodynamic evidence and the realistic engine parameters, the data does not support the hypothesis that the F-16 was destroyed directly by a K-212. The calculated exhaust velocity and overall energy distribution suggest that the missile speed and kinetic capacity were insufficient for interception under the described motions. Therefore, it is more plausible that the incident resulted from an other failure. It could be a mechanical, an operational, or an external motive unrelated to the missile's impact. That was the conclusion that we came at in the report. And for me personally, the project strengthened my understanding of energy transformation, engine performance, and the importance of also connecting engineering models with real world reasoning, to not just have it as a piece of paper, to actually have it in a real world situation. It reminded me that also in aerospace engineering, every number represents a piece of the truth, and together they tell us a story behind the event. Thank you so much for watching and for exploring how thermodynamics helps us uncover what really happened to this F-16.